Hello there and welcome back to the Science Sleepy Minds. Tonight, you are not in your bed. Not really. Tonight, you're 13 billion miles from the nearest cup of coffee, drifting in a darkness so absolute that the sun itself has shrunk to just another star in a field of millions. You can feel nothing out here. No breeze, no temperature, no sound, except for a faint electronic hum coming from a spacecraft roughly the size of a small car, covered in tin foil and running on the radioactive heartbeat of a few pounds of plutonium. That spacecraft is Voyager 1, and right now, in this very moment, it is the most distant human-made object in existence, still whispering data back to Earth at the speed of light, a message that takes nearly a full day to arrive. You are riding shotgun on that whisper, and honestly, you probably would not survive even a single second out here without a spacecraft wrapped around you, because the interstellar medium does not care about your weekend plans. It is a thin, cold, irradiated soup of particles that would very much like you to not exist. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now go ahead and drop a comment telling me where you're listening from tonight and what time it is where you are. I always love reading those. Someone is always tuning in from a place I have never heard of, and that is one of the best parts of doing this. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle in, and the story begins not out here in the black, but back on a pale blue planet, in an era when humans were still figuring out how to make pocket calculators affordable. The year is 1977, and two spacecraft are about to leave Earth with no return ticket. They will fly past giant planets, photograph moons that no human eye has ever seen clearly, and then just keep going, out past the edge of the solar wind, past the boundary where our sun's influence finally gives up, and into a place that scientists had only theorized about in chalkboard equations. What they find out there will be stranger, messier, and more beautiful than anyone predicted. But you are getting ahead of yourself. To understand what Voyager detected at the edge of our solar system, you need to understand the edge itself. And to understand the edge, you need to understand what creates it. So picture this: the sun, that enormous ball of fusing hydrogen sitting at the center of everything you have ever known, is not just producing light and heat, it is exhaling, constantly. A stream of charged particles, protons, electrons, a smattering of helium nuclei, pours outward from the sun's corona at speeds that can exceed 1 million miles per hour. This is the solar wind, and it does not just vanish after passing Mercury or Mars or even Pluto. It keeps going, inflating an enormous bubble around the entire solar system. That bubble is called the heliosphere, and for billions of years it has acted like a cosmic shield, deflecting a significant portion of the dangerous galactic cosmic rays that permeate the Milky Way. You are alive, in part because of this bubble. Every organism that has ever lived on Earth has existed inside it. No human being and no human machine had ever confirmed what lay beyond it until Voyager. Now here is a quirky thing that most people forget. The heliosphere is not a fixed, rigid shell. Scientists still argue whether it is shaped more like a long comet tail stretching behind the sun as it moves through the galaxy, or more like a rounded, squashed sphere. Something closer to a croissant if you can believe that a peer-reviewed astrophysics paper once used the word croissant to describe the structure protecting all life on Earth. The debate is genuinely unresolved. Computer models spit out different shapes depending on which assumptions you feed them, and Voyager's data has only made the argument louder, not quieter. You think about that for a moment. This idea that you have spent your entire life inside a bubble, and humanity did not even confirm the bubble's outer boundary until just a little over a decade ago. The year was 2012, but you will get there in time. Right now you need to go back further, to the peculiar set of circumstances that made Voyager possible in the first place. Because this mission almost did not happen. It took a rare alignment of the planets, literally, a stroke of political luck, a handful of stubborn engineers, and a golden phonograph record that carries the sound of a kiss, the brainwaves of a woman in love, and a greeting in 55 languages, hurtling through the galaxy at 38,000 miles per hour with absolutely no guarantee that anyone or anything will ever play it. The darkness around you hums softly. Voyager's instruments tick and click, measuring things you cannot see. And the story, like the spacecraft itself, pushes forward, always forward, into territory no one has mapped. The story of Voyager begins, as so many great stories do, with someone doing math on a chalkboard and realizing something extraordinary. You rewind to the early 1960s and you find yourself in the office of a young aerospace engineer named Gary Flandreau at the Jet Propulsion Laboratory in Pasadena, California. Flandreau has been given a fairly routine assignment: calculate possible trajectories for missions to the outer planets. He's sketching orbital paths, plotting where Jupiter, Saturn, Uranus and Neptune will be over the coming decades. And somewhere in the middle of all that arithmetic, he notices something remarkable. In the late 1970s, all 4 giant planets will be arranged in a loose arc on the same side of the Sun. This alignment happens roughly once every 176 years. The last time it occurred, Thomas Jefferson was alive, and nobody on Earth had any idea what a spacecraft was. The next time it will happen, everyone listening to this will be long gone. Flandreau realizes that a single probe, launched at the right moment, could use the gravity of each planet as a slingshot to fling itself to the next one, visiting all 4 gas and ice giants in a single mission, lasting about 12 years instead of the 30 or 40 it would take with conventional propulsion. He calls it the Grand Tour, and the name sticks. Now, you might think that NASA heard this idea and immediately threw money at it. You would be wrong. The Grand Tour concept landed on desks during one of the most turbulent periods in American space funding. The Apollo program was winding down, budgets were being slashed, and politicians were far more interested in the space shuttle, which promised to be reusable and economical. Promises that historians still argue whether the shuttle ever truly delivered on. The original Grand Tour proposal called for 2 pairs of spacecraft, 4 in total, built with cutting-edge technology and a price tag that made Congress physically uncomfortable. By the early 1970s, the Grand Tour in its full form was dead, cancelled. The planets were aligning, and Washington did not care. But here is where stubbornness saves the day. Engineers and scientists at JPL refused to let the opportunity vanish entirely. They came back with a stripped-down proposal: just 2 spacecraft, officially approved only for Jupiter and Saturn flybys, with a budget roughly a third of the original Grand Tour estimate. They called the project Mariner Jupiter Saturn, because bureaucracies love names that sound like filing cabinet labels. The spacecraft would be based on the existing Mariner platform modified and upgraded, and they would launch in 1977 to catch the tail end of that planetary alignment window. Congress, somewhat grudgingly, said yes. It was only later, after the name had already become a minor embarrassment, that someone mercifully rebranded the mission. The twin spacecraft became Voyager 1 and Voyager 2, names that actually sounded like they belonged to something historic. You picture the engineers in the mid-1970s, working in buildings that looked less like a futuristic space agency and more like a community college campus in the San Gabriel Valley, because that is essentially what JPL's architecture resembled. They are building 2 identical spacecraft on a budget that, adjusted for inflation, is roughly what a mid-level Hollywood blockbuster costs today. Each Voyager weighs about 1,800 pounds, roughly the weight of a grand piano plus a large dog. The body is a 10-sided bus, an aluminum frame packed with electronics, mounted on a boom that holds the nuclear power source, a radioisotope thermoelectric generator, which converts the heat from decaying plutonium-238 into electricity. No solar panels out here. Past the asteroid belt, the sun is too dim and too far to keep the lights on, so each Voyager carries its own tiny nuclear furnace, and it will keep generating power for decades, though a little less each year as the plutonium slowly dies. The instruments are a marvel of 1970s engineering, which means they are laughably primitive by today's standards, and yet still more than capable of rewriting textbooks. Each spacecraft carries cameras, infrared and ultraviolet spectrometers, magnetometers, plasma detectors, cosmic ray sensors, and a photopolarimeter. The onboard computer has about 69 kilobytes of memory. For context, a single photograph on your phone today takes up more storage space than the entire brain of a Voyager spacecraft. And yet these machines will discover active volcanoes, photograph ring systems in staggering detail, and eventually detect the boundary of the heliosphere. There is a lesson in that, probably something about how limitations breed creativity, but you are too comfortable right now to turn it into a motivational poster. Here is a fringe tidbit that rarely makes it into the documentaries. During construction, engineers realized that the boom holding the magnetometer, a long arm extending away from the spacecraft body to avoid magnetic interference from the electronics, was so delicate that it could be damaged by the acoustic vibrations during launch. Their solution was to design a special canister that would protect the boom and then release it once the spacecraft was safely in space. The mechanism worked, but just barely, and there were genuine nail-biting moments during testing when the whole thing looked like it might fail. One engineer later compared it to trying to pack a fishing rod into a coffee can and then hoping it would spring out perfectly straight while travelling at 17,000 miles per hour. The twin spacecraft sit in clean rooms, wrapped in thermal blankets that shimmer like gold and silver foil. They look fragile, almost homemade, like something a very talented uncle might build in a garage over a long weekend. And in a sense, that is not far from the truth. JPL's culture in the 1970s was famously hands-on, with engineers personally soldering components and testing circuits in ways that would make modern quality assurance teams faint. But these delicate machines are about to do something no human artifact has done before. They're about to leave the solar system, not in a metaphorical sense, not in a poetic sense, but in a measurable, verifiable, data-transmitting sense. They just do not know it yet. Nobody does. And neither for the moment do you. But you are getting there. The spacecraft are almost ready, but there is one final, wonderfully human detail to attend to before they leave Earth forever. Someone has decided that each Voyager should carry a message, a kind of cosmic greeting card, just in case something out there eventually stumbles across one of these little gold-wrapped machines drifting between the stars. The idea is not entirely new. Pioneer 10 and 11, launched a few years earlier, each carried a small gold anodized plaque showing a line drawing of a man and a woman, a diagram of our solar system, and a map using pulsars to pinpoint Earth's location. That plaque had generated both excitement and controversy, partly because the woman in the drawing had no navel, and partly because some people felt that broadcasting our address to unknown aliens was perhaps not the wisest move. But the Pioneer plaque was simple, almost quaint. For Voyager, the ambition would be much grander. You find yourself in a room in early 1977 with Carl Sagan, the astronomer who had become America's most famous science communicator, a man who could make the word billions sound like a lullaby. NASA has asked Sagan to lead a small committee tasked with assembling a message that could represent all of humanity to any extraterrestrial civilization that might find the spacecraft millions of years from now. The medium they choose is a 12-inch gold-plated copper phonograph record, encased in an aluminum cover with a stylus and pictographic instructions for how to play it. The committee has roughly 6 weeks to decide what goes on this record. 6 weeks to represent an entire planet. You can already feel the arguments brewing. The golden record, as it comes to be known, is a time capsule and a love letter, and a slightly desperate prayer all rolled into one. It contains 115 images encoded in analog format, photographs of Earth, its people, its animals, its architecture, its DNA structure. There are greetings spoken in 55 languages, from Akkadian, a language that has been dead for thousands of years, to Wu Chinese, spoken by tens of millions. There is a section of sounds, a mother kissing her baby, the rumble of thunder, the call of a humpback whale, the roar of a rocket launch, the tapping of Morse code. And then there is the music. 27 tracks ranging from Bach's Brandenburg Concerto No. 2 to Chuck Berry's Johnny B. Good to a Navajo night chant to a Pygmy Girl's initiation song from Zaire. The selection process was agonizing, political, and occasionally absurd. Sagan wanted to include the Beatles' Here Comes the Sun, but EMI, the record label, refused to grant permission for interstellar distribution, which remains one of the most beautifully ridiculous sentences in the history of intellectual property law. Now here is where the story takes a more personal turn that most people never hear about. One of the committee members was Anne Druyan, a creative director who would later become Sagan's wife. During the process of assembling the record, Druyan had an idea. They should include the brain waves of a human being, recorded by an EEG machine, compressed and encoded onto the record. She volunteered herself. On June 3rd, 1977, Druyan sat in a lab at New York University with electrodes attached to her head for an hour while she meditated on a series of topics: the history of Earth, the nature of human civilization, what it feels like to be alive. What she did not tell anyone at the time except Sagan was that just 2 days before the recording session, she and Sagan had confessed their love for each other over the phone. They had decided to marry. So when Druyan sat in that lab, thinking about what it means to be human, she was also, by her own later admission, deeply in love and thinking about that too. Her brain waves, encoding that silent private storm of emotion, were pressed into the golden record and launched into space. Somewhere out there, right now, there is a record hurtling through interstellar darkness that carries the neurological signature of a woman falling in love. Scientists still argue whether any alien civilization could ever decode those brainwaves into anything meaningful, but as a poetic gesture, it is almost unbearably beautiful. The record also includes a message from the Secretary General of the United Nations, a greeting from the President of the United States, Jimmy Carter at the time, and a printed message from Carter that reads, in part, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings." It is the kind of statement that sounds grandiose until you remember that the spacecraft carrying it will outlast every building, every city, and possibly every biological descendant of the people who wrote it. The golden record will survive for at least 1 billion years in the vacuum of space, long after the sun has swollen into a red giant and swallowed the Earth whole. Whatever else humanity achieves or fails to achieve, that record will still be drifting, intact, through the galaxy. But let us be honest for a moment, because honesty is important even in a sleepy bedtime story. The chances of the golden record ever being found by an extraterrestrial intelligence are astronomically small. Space is vast beyond comprehension, and the Voyagers are heading into essentially empty corridors between stars. Voyager 1 will not come within spitting distance of another star for about 40,000 years, and even then, it will pass roughly 1.6 light-years from a dim red dwarf called Gliese 445, which is close by cosmic standards, but still an unimaginably huge distance. The record was never really about the aliens, it was about us. It was about the act of trying, the audacity of believing that your existence matters enough to announce it to the universe, even if nobody is listening. And that impulse, that stubbornly hopeful, slightly irrational impulse, is woven into every circuit and every instrument aboard both Voyager spacecraft. They were built by people who believed that knowing what is out there is worth the effort, even if the answer turns out to be silence. You let that thought settle like a blanket. The golden record spins in your imagination, catching a glint of starlight that will never actually reach it. And the countdown to launch is almost here. The summer of 1977 smells like rocket fuel and anxiety. You're standing at Cape Canaveral, Florida, where the air is thick with humidity and the particular kind of nervous energy that only exists when billions of dollars of hardware are sitting on top of a controlled explosion. Here is a fact that trips people up every single time. Voyager 2 launched first. On August 20th, 1977, Voyager 2 climbed into the sky aboard a Titan IIIe Centaur rocket, 16 days before its twin. Voyager 1 followed on September 5th, and despite launching second, it was placed on a faster, shorter trajectory that would allow it to reach Jupiter first. The naming convention was based on arrival order, not launch order, which is exactly the kind of bureaucratic logic that makes you want to lie down, which conveniently you are already doing. The launches themselves were not without drama. Voyager 2's liftoff was nearly scrubbed due to a problem with the launch vehicle, and in the first minutes after separation from the Centaur upper stage, engineers at JPL noticed something alarming. The spacecraft's boom, the one holding the science scan platform, had not fully deployed. For a few tense hours, the team was not sure if the platform carrying the cameras and spectrometers was stuck in a position that would render half the mission's instruments useless. Commands were sent, adjustments were made, and eventually the boom locked into place. But the scare left a mark on the operations team. They were reminded very early that space is a place where small mechanical failures can erase years of work in an instant. Voyager 1's launch went more smoothly, but it carried its own quiet tension. The spacecraft had to be inserted into a precise trajectory, a hyperbolic escape orbit that would carry it past the Moon, past Mars's orbit, and out toward Jupiter. The margin for error was slim. A deviation of even a fraction of a degree during the initial burn could mean missing Jupiter by millions of miles. And unlike a car on a highway, you cannot exactly pull over and ask for directions when you're coasting through the vacuum at 38,000 miles per hour. The navigation team, using computers that had less processing power than a modern washing machine, calculated the trajectory with extraordinary precision. Voyager 1 was on course. Now, the first weeks of any deep space mission are a peculiar blend of elation and tedium. The spacecraft are travelling fast, but space is absurdly large, and Jupiter still nearly 2 years away. During this cruise phase, engineers methodically checked every instrument, calibrated sensors, and tested communication links. The Deep Space Network, a collection of enormous radio antennas stationed in California, Spain, and Australia, positioned so that at least one dish always has a line of sight to any spacecraft in the solar system, locked onto the Voyager's signals, and began the long, patient work of listening. The signal from each Voyager is transmitted at about 23 watts, roughly the power of a refrigerator light bulb. By the time that signal reaches Earth from Jupiter's distance, it has spread out so much that the received power is roughly 20 billion times weaker than the power of a digital watch battery, and yet the Deep Space Network can hear it. That is not magic. That is just very, very good engineering and very, very large antennas. Here is a quirky detail that deserves more appreciation than it gets. Each Voyager spacecraft carries a set of backup systems, because when your machine is 1 billion miles from the nearest repair shop, redundancy is not a luxury, it is survival. There are duplicate computers, duplicate receivers, duplicate command decoders. But here is the charming part. The backup systems on Voyager 2 were not all identical to the primary ones. Some were slightly different designs, on the theory that if a flaw in one design caused a failure, the alternate design might not share that flaw. This philosophy of deliberate asymmetry and redundancy was somewhat unusual for the time, and historians still argue whether it was a stroke of engineering genius or a pragmatic response to budget constraints that forced the team to use whatever spare components were available. Either way, it would prove spectacularly useful years later when Voyager 2's primary radio receiver failed in 1978, just a year into the mission, and the backup receiver, which had its own peculiar quirk of drifting frequency, became the sole communication link for the rest of the spacecraft's life. Every command sent to Voyager 2 from that point on had to account for this frequency drift, a delicate adjustment that the operations team performed thousands of times over the following decades without ever losing contact. It is the kind of quiet, unglamorous heroism that never makes the front page. As the weeks turned into months, the Voyagers settled into their cruise. The sun shrank behind them, slowly but perceptibly. The inner solar system, Mercury, Venus, Earth, Mars, fell away, becoming just another cluster of dots in the rearview mirror that these spacecraft do not actually have. Ahead lay the asteroid belt, which sounds terrifying if your only reference is science fiction movies, where ships dodge tumbling boulders every few seconds. In reality, the asteroid belt is almost comically empty. The average distance between asteroids is about 600,000 miles. Both Voyagers sailed through without incident, without even photographing a single asteroid up close, because there simply was not one nearby enough to bother with. The belt is less a wall of rocks, and more a very sparse neighbourhood where the houses are millions of miles apart. And beyond the belt, something enormous waited. Jupiter, the largest planet in the solar system, a world so massive that you could fit over 1,300 Earths inside it, was pulling the Voyagers toward it with a gravitational embrace that would accelerate them to speeds no rocket engine could achieve on its own. You're about to witness the first alien world up close, and nothing about it will match what the textbooks predicted. The cruise is over, the show is about to begin. You arrive at Jupiter in early March 1979, riding with Voyager 1, and the view is enough to make you forget how to breathe, which out here would be a permanent condition anyway. Jupiter fills your field of vision like a living painting. Bands of cream and rust and ochre swirling in parallel stripes, punctuated by storms the size of entire planets. The Great Red Spot, that iconic anticyclonic storm that has been raging for at least 300 years and possibly much longer, is right there, close enough that you can see its internal structure for the first time. It is not a simple oval. It is a churning layered vortex with smaller storms being pulled into its edges and devoured. A cosmic whirlpool that could swallow Earth twice over and still have room for dessert. The colours are more vivid and more complex than any Earth-based telescope ever hinted at, and scientists watching the images arrive at JPL are literally gasping. This is not an exaggeration. There are accounts of mission scientists standing in front of monitors with their mouths open, unable to form professional sentences. Voyager 1's cameras capture Jupiter's atmosphere in a level of detail that rewrites atmospheric science overnight. The banded structure, long thought to be relatively stable and straightforward, turns out to be a roiling mess of turbulence. Between the major bands, you can see smaller eddies, white ovals, brown barges of descending dry air and lightning bolts on the night side of the planet that are thousands of times more powerful than any lightning on Earth. The atmosphere is mostly hydrogen and helium, but trace amounts of ammonia, methane and water vapour create the riot of colours. One researcher will later describe Jupiter as looking like someone stirred a pot of butterscotch and forgot to turn off the stove for 3 centuries, which is not exactly peer-reviewed language but captures the feeling rather well. But the real surprises are not on Jupiter itself, they're on its moons. Jupiter has a vast family of satellites, we now know of over 90, but 4 of them are large enough to be worlds in their own right. These are the Galilean moons, named after Galileo Galilei, who spotted them through his telescope in 1610 and promptly got in trouble with the Catholic Church for suggesting they orbited Jupiter rather than Earth. Voyager is about to visit all 4, and one of them is going to deliver the single most shocking discovery of the entire mission. You turn your attention to Io, the innermost of the 4 Galilean moons, and something is very wrong with it. Or very right, depending on your perspective. Io is supposed to be a dead, cratered world, like most moons. That is what everyone expects. Instead, Voyager's cameras reveal a surface that looks like a burnt pizza. Splotchy oranges, yellows, blacks and whites, with almost no impact craters anywhere. The absence of craters is the clue. On any geologically dead body, craters accumulate over billions of years. If Io has no craters, something is erasing them. Something is resurfacing the entire moon. And then navigation engineer Linda Morabito, examining an image taken after Voyager 1's closest approach, notices a strange umbrella-shaped plume rising above Io's limb. She has just discovered the first active volcano ever observed on another world. This is a genuine thunderbolt moment in planetary science. Before Voyager, Earth was the only known body in the solar system with active volcanism. Io, it turns out, is the most volcanically active object in the entire solar system, more active than Earth by a wide margin. Its volcanoes spew sulfur and sulfur dioxide hundreds of miles into space, painting the surface in those garish pizza colours and constantly renewing it. The energy source is tidal heating. Jupiter's immense gravity, combined with the gravitational tugging of the other large moons, flexes Io's interior like someone repeatedly squeezing a rubber ball, generating enough friction and heat to melt rock. Scientists had actually predicted this mechanism in a paper published just weeks before Voyager arrived, which is either a stunning coincidence or a reminder that theoretical physics occasionally gets things spectacularly right. Historians still argue whether the prediction truly preceded the observation, or whether informal word about the discovery leaked before the paper was finalised, but the official timeline gives the theorists the win. Europa, the next moon out, offers a completely different mystery. Its surface is a shell of water ice, crisscrossed with reddish-brown cracks that make it look like a hard-boiled egg that someone dropped on the kitchen floor. There are very few craters here too, suggesting a young active surface, and the cracks hint at something moving beneath the ice. Voyager's instruments are not sensitive enough to confirm it, but scientists begin to suspect that beneath Europa's frozen crust lies a global ocean of liquid water, kept warm by the same tidal heating that powers Io's volcanoes. Liquid water, of course, is one of the key ingredients for life as we understand it, and Europa will eventually become one of the most tantalizing targets in the search for extraterrestrial biology. But that is a story for another night. For now, Voyager gives us just enough to dream about it. Ganymede, the largest moon in the solar system, bigger than the planet Mercury, reveals a surface split between ancient dark terrain and younger, grooved light terrain, suggesting some kind of tectonic activity in its past. Callisto, the outermost Galilean moon, is the opposite. a heavily cratered ancient surface that appears to have changed very little in 4 billion years. A museum piece floating in orbit around a planet that devours storms for breakfast. Voyager 1 swings past Jupiter, picking up a gravitational boost that adds roughly 35,000 miles per hour to its speed, bending its trajectory towards Saturn. Voyager 2 arrives at Jupiter 4 months later, in July 1979, confirming and expanding on its twin's discoveries. The data from both encounters will take scientists years to fully analyse, but you are already moving on, because Saturn is calling, and what happens there will change the course of the entire mission. Saturn announces itself slowly, the way truly magnificent things tend to. Weeks before closest approach, the rings begin to resolve in Voyager's cameras, transitioning from the familiar textbook image, a few broad, solid-looking bands, into something far more intricate and far more unsettling in its complexity. You're watching those rings sharpen in real time, and what emerges is not the simple structure astronomers have sketched for centuries. There are hundreds of individual ringlets, thousands even, nested inside one another like the grooves on a vinyl record, separated by gaps of varying widths, some of which contain faint, ghostly material that should not be there according to the prevailing models. The rings are not solid bands. They're vast, flat sheets of ice and rock particles, ranging in size from grains of sugar to houses, all orbiting Saturn in an impossibly thin plane. The entire ring system spans over 170,000 miles in diameter, but is in most places only about 30 feet thick. If you scaled the rings down to the size of a football field, they would be thinner than a razor blade. That is not a metaphor, that is geometry. Voyager 1 arrives at Saturn in November 1980, and the discoveries come so fast that the science team can barely keep up with the data stream. The rings contain structures no one predicted. Spokes, dark radial features that rotate with the rings, and seem to defy the normal laws of orbital mechanics. These spokes appear and disappear over hours, and the leading explanation, that they're caused by tiny charged particles levitated above the ring plane by electromagnetic forces, is still debated among ring scientists today. Historians still argue whether the spokes were technically discovered by Voyager, or whether earlier ground-based observers had caught hints of them that were dismissed as optical artifacts. Either way, Voyager provides the first indisputable images, and they are beautifully strange. The gaps between rings turn out to be governed by gravitational resonances with Saturn's many moons. Tiny shepherd moons, some no bigger than a city, orbit within and alongside the rings, their gravity sculpting sharp edges and maintaining gaps that would otherwise blur and fill in over time. Voyager discovers several of these shepherd moons for the first time, and they are wonderfully odd, irregularly shaped, potato-like objects that look like they were assembled from leftover parts. One of them, Pan, sits inside the Enki gap and has a distinctive ridge around its equator that makes it look like a ravioli, though that description will not become famous until the Cassini mission photographs it more closely decades later. But Saturn's rings, spectacular as they are not the reason Voyager 1 makes the decision that will define the rest of its existence. That reason is Titan, Saturn's largest moon. Titan is the only moon in the solar system with a dense, substantial atmosphere. Thicker than Earth's, in fact, composed mostly of nitrogen, with a haze of organic compounds that give it a smooth, opaque, orange appearance. From a distance, Titan looks like a fuzzy peach. Up close, it looks like a fuzzy peach that is hiding something, and scientists desperately want to know what is underneath that haze. The problem is geometry. To get a close look at Titan, Voyager 1 has to fly a trajectory that passes very near the moon, swooping below Saturn's ring plane. This trajectory gives the spacecraft an excellent view of Titan's atmosphere, its composition, temperature structure, and surface pressure, but it comes with a cost. The gravitational deflection from the close Titan flyby will bend Voyager 1's path sharply upward, out of the ecliptic plane, the flat disk in which all the planets more or less orbit. Once that happens, Voyager 1 will never visit another planet. No Uranus, no Neptune. The grand tour, for this spacecraft at least, ends at Saturn. This is a decision that has been debated and analysed and ultimately accepted long before Voyager 1 arrives. Titan is too scientifically important to skip. Its atmosphere contains complex organic chemistry, methane, ethane, hydrogen cyanide, and a zoo of other carbon-based molecules that some scientists believe resembles the conditions on early Earth before life arose. Studying Titan is, in a sense, studying a frozen laboratory of prebiotic chemistry. The decision is made. Voyager 1 will sacrifice future planetary encounters for a close look at this extraordinary moon. The burden of continuing the grand tour falls entirely on Voyager 2, which will be routed past Saturn on a trajectory that preserves its ability to reach Uranus and Neptune. It is a calculated gamble, a division of labour between twin siblings, and it means that from this point forward, the two Voyagers will have fundamentally different destinies. Voyager 1's Titan flyby reveals that the moon's surface pressure is about 1.5 times that of Earth. You could stand on Titan without a pressure suit, though you would freeze solid almost instantly in the minus 179 degrees Celsius temperatures, and you would suffocate in the nitrogen atmosphere, so perhaps stand is an optimistic verb. The atmosphere is so thick and the gravity so low that if you strapped wings to your arms, you could literally fly by flapping, which is a delightful piece of physics that has nothing to do with Voyager's primary mission, but which you are now going to think about every time someone mentions Titan. The cameras, unfortunately, cannot see through the orange haze to the surface below. That mystery will have to wait for the Huygens probe, which will parachute through Titan's atmosphere in 2005 and land on a surface scattered with ice pebbles smoothed by flowing liquid methane. But Voyager opens the door to that discovery by confirming that Titan's atmosphere is real, complex, and worth returning to. Saturn itself is gorgeous in ways the cameras barely capture. The subtle banding of its atmosphere, the hexagonal storm at its north pole that will not be fully appreciated until Cassini arrives decades later, the delicate colour variations that make it look like a marble dipped in honey. Voyager 1 drinks it all in, transmits every bite, and then follows its new trajectory up and away from the planetary plane, climbing toward the stars. Behind it, Voyager 2 is already on approach, carrying the hopes of every scientist who wanted to see Uranus and Neptune. The baton has been passed. You ride now with Voyager 2, the quieter twin, the one that does not get its name mentioned first, the one whose primary radio receiver broke a year into the mission and has been limping along on a backup with a drifting frequency ever since. Voyager 2 is the underdog, and underdogs, as a general rule, tend to deliver. Its Saturn encounter in August 1981 goes smoothly, confirming many of Voyager 1's findings while adding new details about the ring system and the smaller moons. But Saturn is just a waypoint now. The real prize lies further out, in a region of the solar system that no spacecraft has ever visited, where two enormous worlds of ice and gas spin in cold blue isolation. Uranus is next, and it is going to be weird. The journey from Saturn to Uranus takes 4.5 years, which is a long time to coast through darkness with nothing to photograph. During this cruise, engineers on the ground perform one of the most impressive feats of remote software surgery in the history of spaceflight. They know that Uranus is much dimmer than Jupiter or Saturn. It is twice as far from the Sun, which means Voyager 2's cameras will need longer exposure times to capture usable images. but longer exposures on a spacecraft travelling at tens of thousands of miles per hour will produce blurry photos unless the spacecraft can compensate by slowly rotating to track its target during the exposure. The original flight software was not designed for this manoeuvre, so the team writes new code, tests it on ground simulators, and uploads it to Voyager 2 across 1 billion miles of space, reprogramming the spacecraft's ancient computers to perform a trick they were never built to do. It works. The images from Uranus will be sharp and clear, and this remote upgrade remains one of the finest examples of deep space engineering improvisation ever accomplished. Voyager 2 arrives at Uranus on January 24, 1986, and the first thing you notice is the colour. Uranus is a pale, featureless blue-green, the colour of a faded swimming pool in winter. Compared to the riotous bands of Jupiter and the elegant cream of Saturn, Uranus looks almost boring. Its atmosphere appears eerily smooth, with very little visible cloud structure. This is partly because a thick haze of methane in the upper atmosphere absorbs red light and reflects blue, giving the planet its uniform aquamarine tint, and partly because whatever storms exist are buried deep beneath that haze, invisible to Voyager's cameras. Scientists are initially disappointed by the lack of visual drama, but the instruments tell a far more interesting story than the cameras. Uranus is tilted on its side. Its rotational axis is tipped about 98 degrees from the vertical, meaning it essentially rolls around the Sun like a ball rather than spinning like a top. No one knows for certain why. The leading hypothesis is that a massive collision with an Earth-sized object early in the solar system's history knocked Uranus onto its side, and scientists still argue whether this was a single catastrophic impact or the cumulative result of several smaller ones. This extreme tilt has bizarre consequences. At the time of Voyager's flyby, the planet's south pole is pointed almost directly at the Sun, meaning one hemisphere has been in continuous sunlight for decades while the other has been in continuous darkness. The magnetic field is equally strange. It is tilted 60 degrees from the rotational axis and offset from the planet's centre, as if someone installed the magnet crooked and then forgot about it. This off-kilter magnetosphere creates a corkscrew-shaped tail that spirals behind the planet as it moves through the solar wind, unlike anything seen at Jupiter or Saturn. Voyager 2 discovers 10 new moons orbiting Uranus, bringing the known total at the time to 15. The 5 largest moons, Miranda, Ariel, Umbriel, Titania and Oberon, all named after characters from Shakespeare and Alexander Pope, because astronomers in the 1800s had excellent literary taste. Each reveal unique surfaces. Miranda, the smallest of the 5, is the star of the show. Its surface is a patchwork of wildly different terrains, huge chevron-shaped features, towering cliffs up to 12 miles high, and grooved regions sitting next to cratered plains, as if the moon had been smashed apart and reassembled by a distracted child. One hypothesis suggests Miranda was indeed shattered by a massive impact, and then gravitationally pulled itself back together, with the different terrain types representing the jumbled pieces. Another suggests internal geological processes created the patchwork without any shattering at all. The debate continues, and Miranda remains one of the most visually bizarre objects in the solar system, a world that looks like it was designed by a committee that could not agree on anything. The ring system of Uranus, first detected from Earth in 1977 during a stellar occultation, a star passing behind the planet, is confirmed and detailed by Voyager 2. The rings are thin, dark, and composed of surprisingly large particles mixed with fine dust, very different from Saturn's bright, icy rings. They're also slightly eccentric and inclined, adding to the general theme that everything about Uranus is just a little bit off. After the encounter, Voyager 2 swings onward, picking up another gravitational boost, aimed now at the last and most distant target on its itinerary, Neptune, a world so far from the sun that noon there looks like deep twilight on Earth, is 3.5 years away. The spacecraft has been in space for nearly a decade. Its plutonium is decaying, its power budget shrinking, its backup receiver still drifting in frequency. And yet it pushes on because that is what Voyagers do. Neptune arrives on August 25th, 1989, almost exactly 12 years after Voyager 2 left Earth, and it is immediately clear that this planet has been saving the best surprises for last. Where Uranus was muted and enigmatic, Neptune is vivid and violent. The planet glows a deep, rich sapphire blue, far more intense than Uranus's pale aquamarine, and its atmosphere is alive with features that nobody expected to find on a world receiving roughly 900 times less sunlight than Earth. There is a massive storm in the southern hemisphere, quickly dubbed the Great Dark Spot in conscious homage to Jupiter's Great Red Spot. It is roughly the size of Earth, ringed by bright white clouds of methane ice crystals that race along its edges at staggering speeds. And those speeds are the real headline. Neptune has the fastest winds ever recorded on any planet in the solar system. Measured by Voyager 2's instruments, some atmospheric currents reach speeds of over 1,200 miles per hour, supersonic by Earth standards. This is deeply puzzling. Wind is driven by energy, and Neptune receives almost no solar energy compared to Jupiter or Saturn. Something internal, residual heat from the planet's formation perhaps, or ongoing gravitational contraction, is driving these ferocious winds, but the exact mechanism remains one of the great unsolved problems in planetary science. Scientists still argue whether Neptune's internal heat source is fundamentally different from Jupiter's and Saturn's, or whether the same processes simply manifest differently at Neptune's lower temperatures and smaller scale. Either way, standing on a hypothetical platform in Neptune's atmosphere would be roughly equivalent to standing inside a wind tunnel designed by someone who had a personal grudge against you. Voyager 2's cameras also catch a smaller storm, nicknamed Scooter for the speed at which it races around the planet, and another dark spot further south. The atmosphere is layered and complex, with bands and vortices interacting in ways that atmospheric modelers will spend decades trying to reproduce in simulations. And then, just as quickly as they appeared in Voyager's images, the storms vanish. When the Hubble Space Telescope turns its gaze to Neptune a few years later, the Great Dark Spot is gone. Neptune's atmosphere churns through storms the way you churn through streaming subscriptions, rapidly, unpredictably, and with no apparent loyalty. But the encounter's crown jewel is not Neptune itself. It is Triton, Neptune's largest moon, and it is one of the strangest objects in the solar system. Triton orbits Neptune backward, in a retrograde direction, opposite to the planet's rotation, which is a strong clue that it did not form alongside Neptune, but was captured from somewhere else. The leading theory is that Triton was once a Kuiper belt object, a distant icy body orbiting the Sun independently, that wandered too close to Neptune and was snared by its gravity. If true, Triton is essentially Pluto's cousin, kidnapped and forced into servitude around a giant planet. Historians still argue whether this capture was a gradual process involving a now-lost binary companion, or a more violent event involving atmospheric drag, but the retrograde orbit is the smoking gun either way. Triton's surface is a revelation. It is covered in nitrogen and methane ice, with a pinkish hue from organic compounds, created by ultraviolet radiation breaking down methane. The terrain includes a bizarre landscape nicknamed Cantaloupe Terrain, a vast region of roughly circular dimples and ridges that looks exactly like the skin of a cantaloupe melon, and nobody is entirely sure how it formed. There are frozen lakes of refrozen nitrogen, long cracks, and smooth plains that suggest relatively recent geological activity. The surface temperature is minus 235 degrees Celsius, making Triton the coldest measured surface of any solid body visited by a spacecraft. And yet, against all expectations, Triton is not dead. Voyager 2's cameras capture dark plumes rising from Triton's surface, geysers of nitrogen gas erupting through the ice and shooting material up to 5 miles into the thin atmosphere before the wind carries it downwind in long, dark streaks across the frozen surface. These are cryovolcanoes, cold-weather geysers powered not by molten rock, but by solar heating of subsurface nitrogen ice that vaporizes and blasts through weak spots in the surface. It is volcanism turned inside out, frozen volcanism on a frozen world, and it is happening right now, in real time, as Voyager flies past. The discovery of active geology on a moon this cold and this far from the Sun is one of the most important findings of the entire Voyager mission, because it demonstrates that geological activity does not require proximity to a star. Energy can come from tidal forces, from residual heat, from the simple physics of ice under pressure. The solar system is far more alive than anyone in 1977 imagined. Voyager 2 sweeps past Triton, past Neptune, and follows its gravitational slingshot downward, below the ecliptic plane, heading south and outward. The planetary tour is over. Every giant planet has been visited, every major moon has been photographed, and the data will take decades to fully mine. The spacecraft's cameras have one more task to perform before they are turned off to save power, but that task is still a few months away, and it will have nothing to do with science and everything to do with perspective. For now, Voyager 2 joins its twin in the long, quiet coast toward the edge of the solar system, 2 tiny machines falling away from the Sun at different angles, different speeds, bound for different patches of interstellar space, carrying identical golden records and increasingly divergent stories. The planets are behind you now, the edges ahead. On February 14th, 1990, Valentine's Day, Voyager 1 is approximately 3.7 billion miles from Earth. Its planetary mission has been over for nearly a decade. The cameras have been idle, the spacecraft coasting silently through a region of space where there is nothing to photograph. No moons, no rings, no swirling storms. And then a command arrives from Earth, travelling at the speed of light, taking about 5.5 hours to reach the spacecraft. The command tells Voyager 1 to do something it was never designed to do. Turn around. Point the camera back toward home. Take one last picture. This is Carl Sagan's idea. He has been lobbying NASA for years to use Voyager 1's camera to capture a portrait of the solar system from the outside, a family photo taken from the porch of the Sun's most distant territory. Many at NASA resisted. The images would have no scientific value. The planets would be tiny specks, barely distinguishable from background noise. Pointing the camera back toward the Sun risked damaging the imaging system, and the bandwidth required to transmit the images would take time away from other data. But Sagan persisted with the quiet, relentless charm that made him one of the most persuasive scientists of his generation, and eventually NASA agreed. Voyager 1 rotates its scan platform and takes 60 frames, a mosaic of the inner solar system, capturing 6 of the 9 planets recognized at the time. Mercury is too close to the Sun to distinguish. Mars is lost in scattered sunlight. Pluto is too small and too dim, but Venus, Earth, Jupiter, Saturn, Uranus, and Neptune are all there, tiny points of light suspended in beams of scattered sunlight that streak across the frames like theatrical spotlights on the emptiest stage imaginable. One frame in particular will become one of the most famous photographs in human history. In it, Earth appears as a tiny pale blue dot, less than a single pixel in size, caught in a band of scattered light that makes it look like a mote of dust floating in a sunbeam. The image is not beautiful in any conventional sense. It is grainy, washed out, and if you did not know what you were looking at, you would see nothing meaningful at all. But Sagan looks at it and sees everything. He writes a passage about it that will be quoted for generations. The idea that everyone you have ever loved, every king and peasant, every young couple in love, every saint and sinner in the history of our species, lived out their lives on that tiny speck. He does not say these things to make you feel small. He says them to make you feel connected to every other human, to the planet itself, to the improbable chain of events that led to you existing at all. The pale blue dot image is not science. It is philosophy delivered by a camera with 1970s optics from the edge of the known world. And it reframes the entire Voyager mission in a way that no amount of data about magnetic fields or atmospheric composition ever could. It says, "This is where you came from, and this is how far you have travelled, and look how small and precious it all is from out here." After the mosaic is complete, Voyager 1's cameras are turned off permanently to conserve power. The spacecraft will never take another photograph. From this point forward, it sees the universe only through its instruments, magnetometers, plasma sensors, cosmic ray detectors, tools that measure the invisible. You might find that sad, losing the ability to see, but the spacecraft does not experience sadness. It simply continues, doing what it was built to do, gathering data in the dark. Now you enter the quiet years, the long cruise that stretches across the 1990s and into the 2000s, and there is a temptation to skip ahead, to jump to the dramatic moments at the edge of the heliosphere. But the quiet years matter, because they are the years that prove something essential about the mission, that patience is a form of heroism. The Voyagers are still transmitting. The Deep Space Network is still listening. A small team of engineers and scientists, their numbers dwindling as budgets tighten and careers move on, continues to tend these spacecraft like gardeners maintaining a very old, very distant garden. During this period, the Voyagers are not doing nothing. Their cosmic ray detectors are counting particles. Their magnetometers are mapping the sun's magnetic field at distances where it has never been measured before. Their plasma instruments are tracking the solar wind as it thins and slows, growing weaker with every passing year and every passing astronomical unit. This data is not glamorous. It does not make headlines. But it is building the foundation for everything that will happen next, because the only way to recognize the edge of the solar system is to understand what the interior looks like first. You need a baseline. You need years of normal reading so that when the readings suddenly change, you know something extraordinary has happened. And something extraordinary is about to happen. The solar wind is starting to behave strangely. The numbers are shifting. Voyager 1, out ahead, is approaching a boundary that exists only in theory and in equations. A place where the sun's breath finally falters. The quiet years are ending. The edge is close. To understand what Voyager is about to encounter, you need to understand the anatomy of the heliosphere, and the best way to do that is to imagine blowing a bubble in a bathtub. Your breath is the solar wind, a continuous stream of charged particles flowing outward from the sun at speeds ranging from roughly 250 to 500 miles per second, depending on solar activity. That breath inflates a bubble in the surrounding water, which in this analogy is the interstellar medium, the thin, cold plasma and gas that fills the space between stars. As long as your breath is strong, the bubble holds. But at some point far from your mouth, the force of your breath diminishes. The pressure of the surrounding water pushes back, and the bubble wall reaches an equilibrium. That wall, that boundary where the solar wind finally meets its match, is what the Voyagers are approaching. But the boundary is not a single line. It is a layered transition zone, and the first layer is the termination shock. Picture this. The solar wind is supersonic as it leaves the sun. It barrels outward faster than the speed of sound in that medium. creating a kind of sonic boom in reverse, a standing shock wave where the wind abruptly slows from supersonic to subsonic speeds, compresses, heats up, and becomes turbulent. This is the termination shock, and scientists have predicted its existence for decades. The question is not whether it exists, but where. Models place it somewhere between 75 and 100 astronomical units from the Sun. 1 astronomical unit being the distance from the Earth to the Sun, about 93 million miles. But models are only as good as their assumptions, and the interstellar medium is not cooperating with clean assumptions. Voyager 1, by the late 1990s, is pushing past 70 astronomical units and climbing. Its plasma instrument, the tool best suited to directly measuring solar wind speed and density, has not been working since 1980, a casualty of the Saturn encounter that left a key sensor stuck in an unusable position. This is an important detail, because it means Voyager 1 is approaching the most significant boundary in the solar system partially blind. It can measure magnetic fields, cosmic ray intensities and plasma waves, but it cannot directly measure the solar wind speed. It is like trying to determine when a river reaches the ocean by measuring the temperature and salinity of the water, but not the current speed. You can do it, but the evidence will be indirect, and the interpretation will be messy. Voyager 2, trailing behind and travelling in a different direction, still has a working plasma instrument, which will prove invaluable later. But Voyager 2 is further from the termination shock, and it is Voyager 1 that will arrive first. In 2002 and 2003, Voyager 1 begins detecting anomalous readings. The intensity of certain low-energy charged particles, anomalous cosmic rays, which are thought to originate from interstellar neutral atoms that have been ionized and accelerated at the termination shock, starts to increase. The magnetic field fluctuations become more erratic. Something is changing in the environment around the spacecraft, and some scientists believe Voyager 1 has crossed the termination shock. A team led by Stamatios Krimigis publishes a paper arguing exactly this, based on particle data from 2002. But other teams disagree. They argue that the particle enhancements could be caused by a transient event, a burst of solar activity propagating outward, rather than a permanent crossing of the shock boundary. The debate becomes heated, which in astrophysics means sharply worded peer-reviewed papers rather than raised voices, though some of those papers are sharp enough to leave marks. The confusion arises partly because the termination shock is not static. It breathes. When the sun is more active, pumping out stronger solar wind, the shock is pushed farther out. When the sun quiets down, the shock contracts inward. It is entirely possible for the termination shock to wash over a spacecraft and then retreat, like a wave lapping at your feet on a beach, crossing you and then uncrossing you, leaving you uncertain about which side you are on. Scientists still argue whether Voyager 1 experienced one or more of these back-and-forth crossings in 2002 and 2003, a foxtrot with a boundary that refused to hold still. The definitive crossing comes in December 2004, at approximately 94 astronomical units from the Sun. Voyager 1's magnetometer detects a sudden increase in magnetic field strength, the compression you would expect as the solar wind slams to a halt and piles up against itself. The cosmic ray intensity jumps. The character of the particle environment changes in a way that is consistent with the spacecraft, now sitting in the slower, hotter, turbulent plasma downstream of the shock. This time, most of the scientific community agrees Voyager 1 has crossed the termination shock and entered the heliosheath, the thick, turbulent region between the shock and the outer edge of the heliosphere. Here is a quirky footnote that rarely gets mentioned. When scientists announced the termination shock crossing, some media outlets described it as Voyager leaving the solar system. This is wrong, and it drove the science team slightly mad. Crossing the termination shock is like stepping from the fast-moving centre of a river into the slower, swirling eddies near the bank. You're still in the river. The actual edge, the heliopause where the river meets the ocean, is still years away. But headlines prefer drama to accuracy, and Voyager reaches edge of solar system is a much better headline than Voyager enters transitional turbulent plasma region, even though the latter is what actually happened. You're now in the heliosheath, and the strangeness is just beginning. The heliosheath is not what anyone expected. You're floating in it now alongside Voyager 1, and the best way to describe it is organised chaos, a region where the solar wind, having been abruptly slowed at the termination shock, piles up and churns like water backing up behind a dam. The plasma here is hotter, denser, and more turbulent than the smooth supersonic flow upstream. It is also, as Voyager is about to reveal, structured in ways that existing models completely failed to predict. For years, the standard picture of the heliosheath was relatively simple. The solar wind slows down, gets compressed, flows along the inside of the heliopause, and eventually drains away into the tail of the heliosphere behind the Sun, like exhaust trailing behind a car driving through fog. The magnetic field in this region was expected to be fairly smooth, draping over the heliosphere in long, graceful arcs. It is a tidy picture, the kind of thing that looks great on a PowerPoint slide. Voyager destroys it almost immediately. Starting around 2007, Voyager 1's magnetometer begins detecting something odd. The magnetic field in the heliosheath is not smooth, it is frothy. The field direction fluctuates wildly over short distances, suggesting that the plasma is organised into distinct magnetic structures. Bubbles, essentially, each one roughly 100 million miles across. The science team, led by physicist Merav Ofer, proposes that the Sun's magnetic field, which reverses polarity every 11 years as part of the solar cycle, creates alternating sectors of positive and negative magnetic polarity in the solar wind. When this sectored wind reaches the heliosheath and gets compressed and turbulent, those alternating sectors break up into a foam of magnetic bubbles. Ofer's team calls it a magnetic foam, and the imagery is perfect. You're flying through a cosmic bubble bath, each bubble a self-contained magnetic island with its own field direction, jostling against its neighbours in a slow, churning dance. This discovery matters far more than it might seem at first. The heliosheath is the solar system's last line of defence against galactic cosmic rays, high-energy particles from exploding stars and other violent events elsewhere in the Milky Way. Scientists had assumed that the draped, smooth magnetic field in the heliosheath would act as a coherent shield, deflecting incoming cosmic rays the way a curved windshield deflects rain. But a foam of disconnected magnetic bubbles works very differently. Instead of deflecting cosmic rays in an organised way, the bubbles scatter them, sometimes trapping them temporarily, sometimes letting them through. The shielding effect is real but messier and less predictable than anyone modelled. This has implications for future human space travel beyond the heliosphere, because the intensity and behaviour of cosmic radiation in this region determines how much shielding a crewed spacecraft would need. The answer, courtesy of Voyager, is probably more than we thought. Here is a fringe tidbit that makes the whole picture even more peculiar. Some researchers have suggested that the magnetic bubbles in the heliosheath might occasionally reconnect, a process where opposing magnetic field lines snap together, releasing bursts of energy and accelerating particles. Magnetic reconnection is the same process that drives solar flares on the Sun's surface, and if it is happening throughout the heliosheath, it means this region is not just passively churning but actively generating its own energetic events, small explosions of magnetic energy popping off like tiny firecrackers in the foam. The evidence for this is still indirect, and scientists still argue whether the reconnection events Voyager's instruments detect are locally generated or remnants of activity closer to the Sun that have been carried outward by the solar wind. But the possibility transforms the heliosheath from a quiet buffer zone into something more dynamic, more alive. Voyager 1 also begins detecting unexpected pressure variations in the heliosheath. The plasma pressure is not uniform. It fluctuates in ways that suggest large-scale waves or disturbances propagating through the region, possibly driven by changes in solar activity months or years earlier that are just now reaching this distant boundary. Imagine dropping a stone into a pond and watching the ripples spread outward. Now imagine the pond is billions of miles across, the ripples take years to travel, and you are a spacecraft sitting in the water trying to figure out which ripple came from which stone. That is essentially what the Voyager team is doing with the pressure data, untangling cause and effect across time delays that make the analysis extraordinarily challenging. Meanwhile, Voyager 2 crosses the termination shock on August 30th, 2007, at about 84 astronomical units from the Sun, 10 astronomical units closer than Voyager 1's crossing. This difference is significant. It tells scientists that the heliosphere is not symmetrical. The termination shock is closer to the Sun in the direction Voyager 2 is travelling, which is the southern hemisphere of the heliosphere, and farther out in Voyager 1's northern direction. This asymmetry is likely caused by the local interstellar magnetic field pressing harder on one side of the heliosphere than the other, squishing the bubble like a hand pressing on a balloon. Voyager 2, with its working plasma instrument, provides direct measurements of the solar wind speed dropping from supersonic to subsonic at the shock, something Voyager 1 could not measure directly. The two spacecraft travelling in different directions are essentially performing a stereo measurement of the heliosphere's shape, and what they find is lopsided, dynamic, and far more complex than the textbook diagram suggests. You're deep in the foam now. The bubbles drift around you, each one a magnetic world unto itself. The edge of the heliosphere is somewhere ahead, but the heliosheath is thick, and Voyager still has years of turbulence to push through before it gets there. The magnetic foam hisses and crackles with energy you cannot see, and the data streams home at the speed of light, carrying secrets that are rewriting everything scientists thought they knew about the boundary between our Sun's domain and the galaxy beyond. By 2012, Voyager 1 has been swimming through the heliosheath for nearly 8 years, and the data is starting to do something new. Something that makes the scientists on Earth sit up a little straighter in their chairs and start sending each other emails with too many exclamation points. The magnetic field is still turbulent, still frothy, but the particle environment is shifting in a way that suggests the spacecraft is approaching a transition zone that nobody quite predicted in its exact form. Starting in late July 2012, Voyager 1's cosmic ray detectors register a dramatic change. The intensity of galactic cosmic rays, those high-energy particles originating from outside the solar system, begins to climb sharply. Simultaneously, the intensity of lower-energy particles associated with the solar wind begins to drop. It is as if someone is slowly opening a door. The galactic radiation is flooding in while the solar particles are draining out. This is, broadly speaking, what you would expect as the spacecraft approaches the heliopause, the true outer boundary of the heliosphere. But the details are strange, because the transition is not smooth and final, it stutters. On July 28th, the cosmic ray intensity spikes, and the solar particle intensity plunges, suggesting Voyager has crossed into interstellar space. Then, on August 1st, the readings reverse. Cosmic rays drop back down, solar particles reappear. The spacecraft has apparently popped back inside the heliosphere. It happens again on August 5th, out and then back in. What Voyager 1 has discovered is a region that the science team will call the magnetic highway, and it is unlike anything in the existing models. In this zone, the magnetic field lines from the Sun appear to connect with the magnetic field lines of the interstellar medium, creating open pathways along which particles can travel freely. Solar particles, which have been trapped inside the heliosphere for years, suddenly have an escape route and stream outward along these connected field lines. Galactic cosmic rays, previously deflected by the heliosphere's magnetic barrier, now have a highway inward. The result is exactly what Voyager observes: a rapid exchange of particles in both directions, a two-way traffic flow on a magnetic road that runs along the boundary of the heliosphere. The magnetic highway is a genuinely new discovery. It was not in the models. No theorist had specifically predicted a region where the magnetic field would remain organized in roughly the same direction, still aligned with the Sun's magnetic field, not yet rotated to the interstellar orientation, while simultaneously allowing free passage of particles in and out. It is a boundary layer, a kind of cosmic customs checkpoint where particles are exchanged, but the magnetic architecture has not yet fully changed. And it complicates the already difficult question of when, exactly, Voyager 1 leaves the solar system. Here is the problem, and it is a genuine scientific headache. If you define the edge of the solar system by the particle environment, where galactic cosmic rays dominate and solar particles disappear, then Voyager 1 crossed that edge during one of those stuttering transitions in late July or early August 2012. But if you define the edge by the magnetic field, where the Sun's magnetic field gives way to the interstellar magnetic field with a different direction and possibly a different strength, then Voyager 1 has not crossed yet because the magnetic field in the highway region still looks solar in character. Scientists still argue whether the magnetic highway should be considered part of the heliosphere, part of interstellar space, or something entirely new that belongs to neither category. It is a definitional debate as much as a physical one, and it reveals something humbling. Even after travelling 13 billion miles, we're not entirely sure how to draw the line on a map. The stuttering crossings are fascinating in their own right. Each time Voyager dips into the region of enhanced cosmic rays and depleted solar particles, it stays there for a few days before bouncing back. The simplest explanation is that the heliopause itself is not static. It ripples and undulates in response to changes in solar wind pressure and interstellar medium pressure, like a flag in a gusty wind. The boundary washes back and forth across Voyager's position, and the spacecraft alternately finds itself on one side and then the other. It is a cosmic game of tug-of-war, and Voyager is sitting right on the rope. Here is a quirky detail that deserves attention. The magnetic highway region is extraordinarily thin, cosmically speaking. The entire transition zone that Voyager 1 spends weeks crossing is estimated to be less than 1 astronomical unit thick, roughly the distance from the Earth to the Sun. That sounds large, but remember that Voyager has travelled over 120 astronomical units to get here. The boundary layer is less than 1% of the total distance from the Sun. It is like driving across the entire United States and finding that the border between the country and the ocean is a strip of land thinner than your car is long. The sharpness of this transition surprises scientists, because models had generally predicted a thicker, more gradual boundary region, where the solar and interstellar environments would blend over many astronomical units. The data from the magnetic highway forces a reassessment of how the heliosphere interacts with its surroundings. It is not a clean break, it is not a gradual fade, it is something in between, a narrow, dynamic, surprisingly structured corridor where two cosmic environments meet, negotiate, exchange particles, and maintain an uneasy boundary that shifts with every gust of solar wind and every fluctuation in interstellar pressure. You hover in that corridor now, feeling the galactic cosmic rays tick against your awareness like rain on a window, the solar particles streaming past you in the opposite direction, heading outward into the galaxy for the first time in their existence. The true crossing is immensely close. The magnetic highway stretches beneath you like a bridge between worlds, and then, one day in August, the bridge ends. August 25th, 2012. You do not know it yet. Nobody does. Voyager 1 has been stuttering back and forth across the boundary for weeks, dipping into interstellar particle territory and then retreating, and the science team on Earth is watching the data with the anxious patience of someone waiting for a pot to boil. But on this particular day, the cosmic ray intensity rises one final time and stays high. The solar particle count drops and stays low. The magnetic highway has delivered Voyager 1 to the other side, and this time there is no bounce back. The spacecraft has crossed the heliopause and entered interstellar space. Except nobody realizes it for another year. This is the part of the story that rarely gets the attention it deserves, because it reveals just how difficult it is to recognize a historic moment when you're living inside it. The problem, once again, is the magnetic field. When Voyager 1 crosses the heliopause, the science team expects to see a dramatic change in the direction of the magnetic field, a rotation from the solar field orientation to the interstellar field orientation, which models predict should point in a significantly different direction. But the magnetometer data shows no such rotation. The field strength changes slightly, and the field becomes smoother and more steady, but its direction remains stubbornly close to what it was inside the heliosheath. This is baffling. If the magnetic field has not changed direction, how can you claim the spacecraft has left the heliosphere? Maybe the particle changes are just another temporary fluctuation. Maybe the boundary has shifted again. Maybe Voyager is in some new unknown transition region that nobody has a name for yet. The debate within the science team becomes intense. Ed Stone, the Voyager project scientist who's been with the mission since before launch, is cautious by nature. He is not willing to declare that Voyager has entered interstellar space until the evidence is unambiguous. Don Gurnett, the principal investigator for Voyager's plasma wave instrument, believes the crossing has occurred, but needs one more piece of evidence to prove it. Other team members fall on various sides of the argument. Papers are written, reviewed, argued over. The scientific community watches and waits, occasionally publishing their own analyses that reach conflicting conclusions. It is a beautiful mess of science in action, not the clean, triumphant narrative of discovery that textbooks prefer, but the real, messy human process of people staring at ambiguous data and trying to figure out what it means. The breakthrough comes from an unexpected direction. In April 2013, a massive coronal mass ejection, a burst of solar plasma hurled outward by an explosion on the Sun's surface, reaches Voyager 1's location after travelling for over a year. When this wave of solar plasma arrives, it causes the plasma around the spacecraft to vibrate, to oscillate at a frequency that Voyager's plasma wave instrument can detect. These oscillations are critical because their frequency reveals the density of the plasma surrounding the spacecraft, and the density Gurnett's team measures is roughly 40 times higher than the density of the plasma inside the heliosheath. It matches, almost exactly, the predicted density of the interstellar medium. This is the smoking gun. The plasma around Voyager 1 is not solar, it is interstellar. The spacecraft is immersed in the thin, cold plasma that fills the space between stars, the same medium that has existed in this part of the galaxy for billions of years, long before the Sun was born. Gurnett's team works backward, using the plasma wave data to pinpoint when the density transition occurred, and they arrive at a date. August 25th, 2012. Voyager 1 crossed into interstellar space on that date, and nobody knew for 13 months. The announcement comes on September 12th, 2013, and it is front-page news around the world. Ed Stone, by now in his late 70s, stands before cameras and declares with careful, measured words that Voyager 1 has become the first human-made object to enter interstellar space. The room erupts, the internet lights up. For a brief, shining moment, a spacecraft launched in 1977, with the computing power of a digital watch, becomes the most famous machine on, or rather off, the planet. But the mystery of the magnetic field lingers. Why did the field direction not change at the heliopause? Scientists still argue over this question, and a consensus has proven elusive. One hypothesis suggests that the interstellar magnetic field near the heliopause has been draped and deformed by its interaction with the heliosphere, bending it into an orientation that happens to align with the solar field. Another suggests that the heliopause is not a simple boundary, but a more complex structure where fields from both sides intermingle in a transition layer too thin for Voyager to fully resolve. A third, more radical idea proposes that the models predicting a sharp magnetic rotation were simply wrong, that the interstellar magnetic field in the Sun's neighbourhood points in a direction closer to the solar field than anyone expected, and the lack of rotation is not a puzzle at all but a straightforward measurement of reality. The debate continues in journals and conference halls, and will likely continue until a future mission, with more sophisticated instruments, revisits the boundary. Here is a detail that captures the emotional weight of the moment. When the science team confirmed the crossing, someone on the Voyager operations team noted the distance: 121.7 astronomical units from the Sun. That is roughly 11.3 billion miles. The signal from Voyager 1, travelling at the speed of light, takes about 17 hours to reach Earth. When the spacecraft crossed the heliopause on August 25, 2012, the light carrying that news did not arrive at Earth until the early hours of August 26th, and the team did not recognise what the data meant until September 2013. The most distant journey in human history was confirmed in retrospect, pieced together from fragments of evidence carried home on a whisper of radio waves by a machine the size of a compact car, powered by the slow decay of plutonium, running software that could be updated but never physically touched again. You sit with that for a moment. The boundary has been crossed. You're on the other side. The other side is not what you expected. To be fair, nobody was entirely sure what to expect, because no human instrument had ever been here before. The interstellar medium, the vast ocean of material that fills the space between stars, has been studied from a distance for decades, using telescopes and theoretical models, but direct measurement is a fundamentally different thing. It is the difference between reading about the ocean in a book and dipping your hand into the water, and the water, it turns out, is stranger than the book suggested. The first surprise is the density. Voyager 1's plasma wave measurements indicate that the interstellar plasma near the heliopause has a density of about 0.055 electrons per cubic centimetre. That sounds impossibly sparse, and it is by any earthly standard. The air in your room right now contains roughly 10 quintillion molecules per cubic centimetre, but by the standards of what scientists expected in the local interstellar medium, 0.055 is actually on the higher end of predictions. Some models had suggested densities closer to 0.04 or even lower. The slightly higher than expected density tells scientists something important about the environment the Sun is currently moving through. It is a bit denser than the average interstellar medium, which is consistent with the Sun being located near the edge of a structure called the local interstellar cloud. A warm, partially ionized wisp of gas roughly 30 light-years across that the solar system entered somewhere between 44,000 and 150,000 years ago and will exit sometime in the next few thousand years. You are, cosmically speaking, passing through a cloud, and Voyager is now measuring that cloud from the inside. The second surprise is the pressure. The total pressure of the interstellar medium near the heliopause, a combination of thermal pressure, magnetic pressure, and the pressure from cosmic rays, is higher than models predicted. This matters because it is the pressure of the interstellar medium that determines the size and shape of the heliosphere. Higher external pressure means the heliosphere is being squeezed harder than expected, which means the protective bubble around the solar system is smaller than some models suggested. Scientists still argue about the exact implications. Some interpret the high pressure as evidence that the local interstellar cloud is itself being compressed by a neighbouring structure. Perhaps the expanding shell of a nearby supernova remnant, or the pressure from the hot gas that fills the local bubble, a cavity in the interstellar medium roughly 300 light-years across that was carved out by a series of supernova explosions millions of years ago. You're inside a cloud, inside a bubble, inside a galaxy, and every layer has its own pressure and its own story. Here is where things get genuinely unsettling for anyone who cares about the long-term habitability of Earth. The heliosphere is a cosmic shield. It deflects a significant fraction of the galactic cosmic rays that would otherwise bombard the inner solar system. If the heliosphere were to shrink dramatically, due to increased interstellar pressure or a weakening of the solar wind during a period of low solar activity, the cosmic ray flux at Earth would increase. Higher cosmic ray flux means more secondary radiation in the atmosphere, which could affect cloud formation, ozone chemistry, and possibly even mutation rates in living organisms. There is a fringe but persistent line of research suggesting that past variations in cosmic ray intensity, driven by the solar system's passage through different interstellar environments, may have influenced Earth's climate and even the pace of biological evolution over millions of years. Historians of science still argue whether this cosmic ray climate connection is a genuine discovery or a case of correlation masquerading as causation. But Voyager's data about interstellar pressure adds a tangible, measured data point to the conversation. The third surprise is the structure. The interstellar medium near the heliopause is not uniform. Voyager 1 detects variations in plasma density over relatively short distances, suggesting that the medium is clumpy, textured, and far from the smooth, featureless expanse that the simplest models depict. These density variations may be caused by turbulence in the interstellar medium, or by the complex interaction between the heliosphere and its surroundings, or by structures in the local interstellar cloud that are smaller than any telescope can resolve from Earth. Whatever their origin, they paint a picture of interstellar space as a place with geography. Subtle, invisible geography, but geography nonetheless. There are denser patches and thinner patches, warmer zones and cooler zones, regions where the magnetic field is stronger and regions where it is weaker. It is not the empty void that popular imagination suggests. It is a landscape, and Voyager is the first explorer to walk through it with instruments capable of reading its terrain. The magnetic field on the other side of the heliopause is also revealing. Its strength is roughly consistent with predictions, about 0.4 to 0.5 nanotesla, which is thousands of times weaker than Earth's magnetic field, but still enough to exert a meaningful influence on the charged particles and plasma in the interstellar medium. The direction, as we discussed, remains frustratingly close to the solar field direction, which means either the interstellar field has been heavily distorted by the heliosphere, or the models about its expected direction were wrong. New data from Voyager continues to trickle in, but the magnetic field puzzle remains one of the mission's most enduring open questions. You drift through this structured, pressurized, unexpectedly complex environment, and you realize something that shifts your perspective. The solar system is not floating in a void. It is moving through a medium, swimming through an ocean of plasma and magnetic fields and cosmic rays, and that ocean pushes back. The heliosphere is not just a bubble, it is a negotiation, a constant dynamic balance between the sun's outward push and the galaxy's inward press. And for the first time in human history, You have instruments on both sides of that negotiation, measuring the terms of the agreement. The data keeps flowing, 17 hours per transmission at the speed of light, and each transmission carries another small piece of the galaxy's portrait, painted 1 pixel at a time by a machine that left Earth before most people listening to this were born. 6 years after Voyager 1 slipped through the heliopause, its twin finally catches up. On November 5th, 2018, Voyager 2 crosses into interstellar space at a distance of approximately 119 astronomical units from the Sun, about 2.5 astronomical units closer than Voyager 1's crossing point, but in a completely different direction. Voyager 1 exited the heliosphere heading northward relative to the ecliptic plane, roughly in the direction of the constellation Ophiuchus. Voyager 2 exited heading southward, roughly toward the constellation Parvo. The two spacecraft have effectively punched holes in opposite sides of the heliosphere, and the comparison between their readings is one of the most valuable datasets in heliophysics. And this time, there is a crucial advantage. Remember that broken plasma instrument on Voyager 1, the one that has been dead since 1980? Voyager 2's plasma science experiment is still working. For the first time, a spacecraft crosses the heliopause with the ability to directly measure the speed, density, and temperature of the plasma on both sides of the boundary. This is the measurement that scientists have been craving for decades, the one that Voyager 1 could only approximate through indirect methods, and the results are illuminating. Voyager 2's plasma instrument reveals that the heliopause crossing is remarkably sharp. The solar wind plasma, which has been flowing outward at reduced speeds through the heliosheath, drops to effectively zero within a distance of less than 1 day's travel, roughly 1 million miles or so. Simultaneously, the interstellar plasma appears, denser and cooler, filling the space that the solar wind has vacated. The transition is not gradual, it is a wall. One moment you're in solar plasma, the next you're in interstellar plasma, and the boundary between them is thinner and cleaner than most models predicted. This sharpness suggests that the heliopause is maintained by a strong pressure balance between the two media, a taut membrane stretched between the outward push of the dying solar wind and the inward press of the interstellar medium. Here is where the comparison between the two crossings becomes truly fascinating. Voyager 1's crossing in 2012 showed those stuttering back and forth fluctuations, the spacecraft dipping in and out of interstellar particle territory for weeks before the final crossing. Voyager 2's crossing is much cleaner. There is some variability in the days leading up to the transition, but the actual heliopause crossing is a single definitive event. The spacecraft passes through and does not come back. Scientists still argue whether this difference reflects genuine structural variation in the heliopause. Perhaps it is more rippled or unstable in the direction Voyager 1 travelled, or whether it is a temporal effect, driven by different solar activity conditions at the time of each crossing. The Sun was near solar maximum during Voyager 1's crossing and closer to solar minimum during Voyager 2's, which means the solar wind pressure was different in each case, potentially affecting the stability of the boundary. The magnetic field at Voyager 2's crossing behaves similarly to Voyager 1's, which is both reassuring and frustrating. The field strength increases slightly as the spacecraft crosses the heliopause, and the field becomes smoother and more laminar, but once again, there is no dramatic rotation in field direction. The interstellar magnetic field, as measured by both Voyagers, appears to be oriented in roughly the same direction as the solar magnetic field in the outer heliosheath. This consistency across two widely separated crossing points strengthens the hypothesis that the interstellar field near the Sun has been draped and aligned by its long interaction with the heliosphere, but it does not definitively rule out other explanations. The magnetic field mystery, it seems, is not a fluke of Voyager 1's location. It is a feature of the boundary itself, One particularly intriguing finding from Voyager 2's crossing is the detection of a boundary layer just inside the heliopause, a thin region where the plasma appears to be a mixture of solar and interstellar material, as if the two environments are leaking into each other at the very edge. This layer is not thick, perhaps a few million miles at most, but its existence suggests that the heliopause is not perfectly sealed. There are processes, perhaps magnetic reconnection, perhaps diffusion, perhaps some instability at the boundary, that allow material to cross from one side to the other. The heliosphere is not a hermetic bubble. It is a permeable membrane, and the interstellar medium is slowly, gently seeping in. Here is a quirky detail that highlights just how different the two crossings are despite their broad similarities. The plasma density that Voyager 2 measures just outside the heliopause is somewhat different from what Voyager 1 measured. This is not necessarily surprising. The two spacecraft are in different regions of the interstellar medium, separated by tens of astronomical units, but it reinforces the idea that the local interstellar environment is not uniform. There are density gradients, possibly related to the structure of the local interstellar cloud or to the heliosphere's own influence on its surroundings. The heliosphere, after all, is not just sitting passively in the interstellar medium. It is ploughing through it at roughly 52,000 miles per hour as the Sun orbits the centre of the Milky Way. This motion creates a bow wave or compression region ahead of the heliosphere, similar to the wave a boat pushes through water. Whether this compression steepens into a true bow shock, a sonic boom in the interstellar medium, is another open question that scientists still argue about, with some models saying yes and others saying the Sun is moving just barely too slowly for a full shock to form. Two spacecraft, two crossings, two different directions, two different solar activity conditions, and yet a consistent picture is emerging. The heliopause is thin, sharp, and dynamic. The interstellar medium is structured and pressurized. The magnetic field transition is subtle and mysterious, and the heliosphere itself is a living, breathing, leaking entity that negotiates its existence with the galaxy in real time. You now have scouts on the outside, two of them, and they are still talking. Now that both Voyagers are outside the heliosphere, they have become something they were never originally designed to be: cosmic ray observatories. They're cosmic ray subsystem instruments, built in the 1970s to study energetic particles in the magnetospheres of Jupiter and Saturn, are now measuring the full, unshielded intensity of galactic cosmic rays for the first time in human history. Inside the heliosphere, these particles were partially deflected and modulated by the solar wind and its embedded magnetic field. Out here, there is no filter. Voyager is standing in the rain without an umbrella, and the rain is made of atomic nuclei travelling at nearly the speed of light. Galactic cosmic rays are not gentle. They are the shrapnel of the universe's most violent events: supernova explosions, the jets of black holes, the shock waves where galaxies collide. When a massive star explodes, it sends a blast wave ripping through the surrounding interstellar medium, and charged particles caught in that wave get bounced back and forth across the shock front, gaining energy with each crossing like a ball bouncing between two converging walls. This process, called diffusive shock acceleration, can boost protons and heavier nuclei to energies millions of times greater than anything achievable in a particle accelerator on Earth. These particles then wander through the galaxy for millions of years, their paths bent by interstellar magnetic fields, until some of them happen to encounter our little corner of the Milky Way and slam into the heliosphere. Most are deflected or slowed by the solar wind, but outside the heliosphere, Voyager sees them all, the full spectrum, the unfiltered galactic weather. The measurements are confirming and refining decades of theoretical predictions. The cosmic ray intensity outside the heliosphere is roughly consistent with what models predicted, but the details matter. The energy spectrum, the distribution of cosmic rays across different energy levels, shows features that constrain models of how these particles are accelerated and transported through the galaxy. Low-energy cosmic rays, which are most strongly affected by the heliosphere's shielding, and therefore hardest to study from inside it, are now measurable for the first time. These low-energy particles carry information about the most recent supernova activity in the Sun's galactic neighbourhood, because they have not been travelling long enough for their energies to be scrambled by repeated scattering off interstellar magnetic field irregularities. They are, in a sense, fresh news from the galaxy, and Voyager is reading the morning paper. Here is a historical fact that puts the cosmic ray measurements in perspective. The existence of cosmic rays was first confirmed in 1912 by Austrian physicist Victor Hess, who carried electroscopes up in a balloon to show that the ionizing radiation in the atmosphere increased with altitude, proving it came from space rather than from the ground. Hess won the Nobel Prize for this work in 1936. For over a century since his discovery, every measurement of cosmic rays has been taken from inside the heliosphere, filtered through the Sun's magnetic influence. Voyager's measurements outside the heliosphere are, in the most literal sense, the first unfiltered cosmic ray data in the history of the field. Hess would probably be speechless, though given that he routinely rode in open basket balloons to altitudes where the temperature dropped below -30 degrees, he was clearly not a man who was easily rattled. Scientists still argue about what the cosmic ray data tells us about the large-scale structure of the galaxy. One ongoing debate concerns the so-called cosmic ray gradient, how the intensity of cosmic rays changes with distance from the heliosphere. If cosmic ray sources are distributed unevenly through the galaxy, you would expect the intensity to vary depending on which direction you look. Voyager 1 and 2, heading in different directions, should in principle see slightly different cosmic ray intensities if there is a significant gradient. So far, the differences between the two spacecraft are small, suggesting that the cosmic ray distribution is relatively uniform in the Sun's local neighbourhood. But the measurements are limited by the fact that both Voyagers are still very close to the heliosphere in galactic terms, just barely outside the front door, peeking around the corner. A spacecraft that travelled hundreds or thousands of astronomical units from the Sun might see a very different picture. That spacecraft does not exist yet, but the Voyager data is helping to design it. The cosmic ray findings also carry a sobering implication for human space exploration. Any crewed mission beyond the heliosphere, or even deep into the outer heliosheath, would face the full brunt of galactic cosmic radiation. This radiation is fundamentally different from the solar energetic particles that threaten astronauts in near-Earth space. Solar particles are mostly protons with energies that can be blocked by a few centimeters of shielding material. Galactic cosmic rays include heavy nuclei, iron, silicon, carbon, travelling at such extreme energies that they punch through conventional shielding like bullets through paper. When these heavy nuclei hit shielding material, they produce showers of secondary particles that can be even more damaging than the original cosmic ray. The only effective protection strategies are either absurdly thick shields, meters of material, which would make a spacecraft impossibly heavy, or active magnetic shielding that deflects charged particles, a technology that exists in concept but not yet in practice. Voyager's cosmic ray data provides the benchmark against which all future shielding designs must be measured. Here is a quirky thought that occasionally surfaces in discussions about deep space radiation. Some researchers have half-seriously proposed that the ideal material for cosmic ray shielding might be water, because it is rich in hydrogen, which is particularly effective at absorbing secondary neutrons produced by cosmic ray impacts. A crewed interstellar spacecraft might, in theory, surround its habitat module with a thick shell of water, serving simultaneously as radiation shielding, drinking water, and a rather impressive swimming pool. Whether this is practical engineering or engineering fantasy is a question that future generations will have to answer, but Voyager's measurements of what is waiting out there make the question feel a little more urgent. The cosmic rain continues and the Voyagers count every drop. Among all the data streaming back from Voyager 1, one particular detection has captured the imagination of scientists and the public alike, perhaps because it appeals to something deeply human, the idea of listening to the universe and hearing it hum. In 2017, the Voyager Plasma Wave Science team, led by Stella Ocker, a doctoral student at Cornell University at the time, identifies something extraordinary in the data. Between the occasional bursts of plasma oscillation caused by solar events propagating outward, there is a faint, persistent, narrow band signal in the plasma wave data. It is not noise. It is not an instrument artifact. It is the sound of the interstellar medium itself, vibrating at a low, steady frequency. A hum, continuous and unrelenting, like the barely audible drone of a refrigerator in a quiet house at 3 a.m. This interstellar hum is technically a plasma oscillation, a vibration of the electrons in the interstellar plasma at a frequency determined by the local electron density. The frequency is extraordinarily low, roughly 3 kHz, which is within the range of human hearing if you could somehow convert the plasma wave directly into a sound wave, though it would sound like a faint, thin tone, not particularly musical, not particularly dramatic. But its significance is enormous, because it provides a continuous real-time measurement of the interstellar plasma density along Voyager 1's path. Before this discovery, the plasma density could only be measured during sporadic events, those coronal mass ejections and solar shock waves that occasionally rattled the interstellar medium and caused detectable plasma oscillations. Between those events, which might be separated by months or years, the plasma density was essentially unknown. The hum fills in the gaps. It is always there, always measurable, always whispering the density of the medium through which Voyager is travelling. And what the hum reveals is that the interstellar medium is not static. The plasma density fluctuates slowly over time and distance, rising and falling in gentle undulations that suggest the presence of low-frequency waves or turbulence in the interstellar medium. These fluctuations are subtle, changes of perhaps 10 or 20% over periods of months, but they are real, and they represent the first direct detection of the fine-scale structure of the interstellar plasma. It is as if you have been flying over an ocean in the dark, unable to see the surface, and someone has given you an altimeter that reveals the waves below. The ocean is not flat. It never was. The discovery of the hum also provides an independent check on the plasma density measurements derived from the sporadic oscillation events. The two methods agree well, which gives scientists confidence that both are measuring the same physical quantity accurately. This cross-validation is important because it strengthens the case that Voyager is genuinely immersed in interstellar plasma and not in some exotic boundary layer or heliospheric remnant. The hum is the interstellar medium's signature, its background music, and it is unmistakably different from anything detected inside the heliosphere. Here's a historical parallel that adds a layer of poetry to the discovery. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, detected a faint, persistent microwave signal coming from every direction in the sky. They could not explain it. They checked their equipment, cleaned pigeon droppings from their antenna, and still the signal persisted. It turned out to be the cosmic microwave background radiation, the afterglow of the Big Bang, a hum left over from the birth of the universe itself. Penzias and Wilson won the Nobel Prize. Voyager's interstellar hum is obviously a very different phenomenon, operating on completely different physical principles, but there is a resonance, if you will pardon the pun, between the two discoveries. Both involve detecting a faint, persistent signal that reveals the fundamental nature of the environment. Both were initially subtle enough to be mistaken for noise, and both transform our understanding of the medium we exist within, whether that medium is the cosmic microwave background permeating all of space, or the interstellar plasma permeating the galaxy. Scientists still argue about the exact origin of the density fluctuations that the hum reveals. One hypothesis attributes them to turbulence generated by the heliosphere's motion through the interstellar medium. Essentially, the sun is stirring the plasma as it moves, creating a wake of density variations. Another hypothesis suggests the fluctuations are intrinsic to the interstellar medium, part of a vast cascade of turbulence generated by supernova explosions and stellar winds throughout the galaxy, with energy flowing from large scales down to the tiny scales that Voyager can detect. A third, more speculative idea connects the fluctuations to the passage of weak interstellar shock waves from distant astronomical events. Each hypothesis makes different predictions about the statistical properties of the density variations, their amplitude, their correlation length, their spectral slope, and as Voyager accumulates more data over longer baselines, the measurements should eventually discriminate between them. But for now, the hum keeps humming and the debate continues. Here is a fringe detail that makes the hum feel almost personal. When Ocker and her colleagues published their findings, they included an audio rendering of the plasma wave data, pitch shifted into a comfortable hearing range and time compressed so that months of data could be heard in seconds. The result is eerie and beautiful, a low wavering drone punctuated by occasional brighter tones when solar events excite the plasma. It sounds, more than anything, like a recording from the bottom of the ocean, or like wind blowing across the mouth of a vast empty bottle. Media outlets played the recording, and millions of people heard for the first time the sound of interstellar space. It is not silence out there. It is a hum, faint, persistent, ancient, and ongoing, vibrating at a frequency set by the density of matter between the stars, a note that has been playing since long before the sun existed and will continue long after it is gone. You listen to that hum now, letting it settle into the rhythm of your breathing. It is almost meditative, this idea that the emptier spaces in the universe are not truly empty, that even the void between stars has a voice if you bring the right instrument to hear it. The hum continues, but the instrument listening to it is dying. This is the part of the story that nobody on the Voyager team likes to talk about, but everyone thinks about constantly. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, RTGs, that convert the heat of decaying plutonium-238 into electricity. When the spacecraft launched in 1977, each RTG produced about 470 watts of electrical power, enough to run a handful of modest household appliances. But plutonium-238 has a half-life of 87.7 years, which means that every 87.7 years, half of the remaining plutonium decays into non-useful daughter products, and the power output drops accordingly. By 2025, each Voyager's RTG is producing roughly 220 watts, less than half the original output, and the decline is relentless, predictable, and unstoppable. There is no way to refuel a spacecraft that is over 15 billion miles away. The plutonium will keep decaying, the power will keep dropping, and one by one the instruments will be turned off. This is not a future problem, it is a present one, and it has been for years. The Voyager engineering team has been performing a slow, painful triage since the early 2000s, deciding which instruments to keep running and which to sacrifice. The cameras, as you know, were turned off in 1990 after the pale blue dot portrait. The ultraviolet spectrometer was turned off. The the infrared spectrometer was turned off. Various heaters that kept instruments and fuel lines from freezing have been switched off one by one, each decision carrying the risk that something critical might get too cold and fail. The spacecraft are now operating at temperatures well below their original design limits, and the fact that they still function at all is a testament to the over-engineering of 1970s era JPL hardware and perhaps a small amount of cosmic luck. By the mid-2000s, each Voyager has only a handful of instruments still operating. The magnetometer, the cosmic ray subsystem, the plasma wave instrument, and the low-energy charge particle detector are among the survivors on Voyager 1. Voyager 2 retains a similar complement plus its working plasma science instrument, that precious sensor that Voyager 1 lost decades ago. Each year, the engineering team reviews the power budget and makes agonizing decisions about what to cut next. These are not abstract engineering choices. Each instrument represents a scientific investigation, a team of researchers, decades of data continuity. Turning off an instrument means ending a measurement that can never be resumed, closing a window on the universe that will not reopen until some future mission, if one is ever built, reaches the same region of space. Here is a detail that captures the human weight of these decisions. The engineers who manage the Voyager power budget have compared the process to hospice care. You're not trying to save the patient, you're trying to make the remaining time as meaningful as possible. Every watt matters, every decision about whether to keep a heater running or let a fuel line risk freezing is a calculation about extending the mission by months or years. In 2019, the team made the decision to turn off the heater for the cosmic ray subsystem on Voyager 2, allowing the instrument to cool to temperatures far below its rated operating range. It kept working. Nobody's entirely sure why. The leading theory is that the instrument's components are simply more robust than the specification suggested, or that the gradual cooling allowed the electronics to adapt in ways that rapid cooling might not have permitted. Scientists still argue whether this kind of beyond-spec survival is replicable or just fortunate, but either way, the cosmic ray subsystem continues to count galactic particles in the cold. The communication link is also fraying. Each Voyager transmits at about 23 watts. Remember, the power of a refrigerator light bulb, using a high-gain antenna dish 3.7 meters across, aimed at Earth. The signal, by the time it reaches the Deep Space Network's 70-meter antennas on the ground, is fantastically weak. The data rate has been reduced over the years from its peak of 115.2 kilobits per second during the planetary encounters to a current rate of about 160 bits per second for Voyager 1 and even lower for Voyager 2. At 160 bits per second, transmitting a single smartphone photograph would take well over a day. But the Voyagers are not sending photographs anymore. They are sending numbers, magnetic field readings, particle counts, plasma wave frequencies, and for those, 160 bits per second is enough. There is a quirky operational detail that illustrates how intimate the relationship between the ground team and the spacecraft has become. Because Voyager 2's backup receiver has that drifting frequency, every command sent to the spacecraft must be carefully tuned to account for the drift. The operations team has been doing this for over 4 decades, adjusting the frequency of each uplink signal based on predictions of where the receiver will be tuned at the moment the signal arrives, hours later, after crossing billions of miles of space. It is like trying to hit a moving target with a dart thrown from another continent, except the dart travels at the speed of light and the target's movements are governed by the thermal characteristics of a 47-year-old radio receiver that nobody can physically inspect. The fact that they have never lost contact is remarkable. Eventually, probably sometime in the early to mid-2000s, the power will drop below the threshold needed to run even a single science instrument. The last data will be transmitted, the last bits will be received, and the spacecraft will go silent. The Deep Space Network will listen for a while, hoping for a stray signal, and then it will turn its antennas to other targets. Voyager will still be out there, still moving, still carrying its golden record, but it will be deaf and mute. A message in a bottle with no one left to read the waves. You feel the weight of that approaching silence, but not yet, not tonight. Tonight the instruments are still running, the hum is still audible, and there are still things to learn. The data that Voyager continues to send home is not just a record of where it has been, it is a blueprint for where humanity might go next. Every measurement of cosmic ray intensity, every reading of interstellar plasma density, every mapping of magnetic field direction feeds into the design requirements of future missions that aim to follow in Voyager's wake. Faster, smarter, and with instruments that would make Voyager's 1970s-era detectors look like tin cans and string. The most ambitious of these proposed missions is the Interstellar Probe, a concept that has been studied by NASA and Johns Hopkins Applied Physics Laboratory for over a decade. The idea is conceptually simple and technically daunting. Send a spacecraft to a distance of at least 1,000 astronomical units from the Sun, roughly 8 times farther than Voyager 1 is now, within a mission lifetime of about 50 years. At that distance, the spacecraft would be well beyond the influence of the heliosphere, deep enough into the interstellar medium to measure its properties without any contamination from solar effects. It would carry modern instruments, high-resolution plasma analyzers, magnetometers with sensitivity orders of magnitude better than Voyager's, dust detectors, neutral atom imagers, and possibly even a telescope to look back at the heliosphere from the outside, mapping its shape directly for the first time. The engineering challenges are formidable. To reach 1,000 astronomical units in 50 years, the spacecraft would need to travel at roughly 7 to 10 times Voyager's current speed. No existing rocket can provide that kind of velocity. The leading proposals involve using a close solar flyby, a maneuver called an Oberth maneuver, where the spacecraft dives close to the Sun and fires its engines at the point of maximum gravitational acceleration, extracting enormous energy from the Sun's gravity well. Some designs call for a solar sail, a large reflective surface that uses the pressure of sunlight itself to accelerate continuously, achieving speeds that chemical rockets cannot match. Others propose using nuclear electric propulsion, where a small nuclear reactor powers an ion engine that provides gentle but sustained thrust over years. Each approach has its advocates, its skeptics, and its unresolved technical problems, and scientists still argue which combination of technologies offers the best balance of speed, cost, and reliability. Voyager's data directly informs these designs. The cosmic ray measurements tell engineers how much radiation shielding the spacecraft's electronics will need. The plasma density measurements help determine what kind of plasma instruments should be carried and how sensitive they need to be. The magnetic field data constrains models of the interstellar medium that mission planners use to predict what the spacecraft will encounter at distances Voyager will never reach. Without Voyager's ground truth, these future mission designs would be based entirely on theory and remote observation, informed guesses rather than measured reality. Voyager has turned guesses into engineering requirements, and that is perhaps its most practical legacy. Here is a historical fact that puts the Interstellar Probe concept in context. When Voyager launched in 1977, the fastest spacecraft ever built was Pioneer 10, which was travelling at about 30,000 miles per hour relative to the Sun. Voyager 1, boosted by its gravitational slingshots at Jupiter and Saturn, currently moves at about 38,000 miles per hour. The Interstellar Probe, depending on the final design, would need to travel at 200,000 to 400,000 miles per hour. That is a leap comparable to going from a horse-drawn carriage to a commercial airliner, and it would need to be achieved within a single generation of spacecraft development. Whether this is realistic is a matter of ongoing and occasionally heated debate within the aerospace community. There are also more exotic proposals that Voyager's data inspires, even if they remain firmly in the realm of theoretical exploration. One concept involves using the Sun itself as a gravitational lens. Einstein's general relativity predicts that the Sun's gravity bends light passing near it, focusing it to a point roughly 550 astronomical units away. A spacecraft positioned at that focal point could, in theory, use the entire Sun as a telescope of unimaginable resolution, capable of imaging the surfaces of exoplanets in other star systems. Voyager will pass through the gravitational focal region on its outward journey, though its instruments are entirely incapable of exploiting the effect. But the concept, first detailed by physicist Slava Turyshev, has gained traction in recent years, and Voyager's measurements of the interstellar medium along the path to the focal point help assess whether interstellar plasma and dust would degrade the lensing effect. Early indications suggest the effect is usable, which is quietly thrilling for anyone who dreams of seeing the surface of a planet orbiting another star. Here is a quirky and somewhat philosophical tidbit. Some researchers have pointed out that Voyager, despite being humanity's most distant explorer, has covered a truly negligible fraction of the distance to even the nearest star. Proxima Centauri is about 268,000 astronomical units away. Voyager 1, at roughly 165 astronomical units as of the mid-2000s, has travelled about 0.06% of that distance in nearly 50 years. At its current speed, it would take over 70,000 years to reach Proxima Centauri, if it were heading in that direction, which it is not. The interstellar medium that Voyager is exploring is essentially the Sun's front porch. The galaxy is the entire continent beyond, and yet that front porch has already revealed enough surprises: the magnetic foam, the sharp heliopause, the interstellar hum, the density fluctuations, to rewrite textbooks and redesign missions. Imagine what the continent holds. You feel a pull toward that future, toward spacecraft that do not yet exist, missions that have not yet been funded, discoveries that have not yet been made, but all of them trace their lineage back to two gold-wrapped machines launched from Cape Canaveral in the summer of 1977, built by people who believed the unknown was worth reaching for. The Voyagers are heading in different directions now, and they will never meet again. Voyager 1 is travelling at about 38,000 miles per hour relative to the Sun, heading generally toward the constellation Ophiuchus, though the specific stars in that region are so far away that heading toward is a generous description of a journey that will take tens of thousands of years. In roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of Gliese 445, a dim red dwarf star in the constellation Camelopardalis that is currently moving toward the Sun and will, by that time, be one of our closer stellar neighbours. Voyager 1 will not stop there. It cannot stop. It has no fuel for braking, no engine capable of decelerating from interstellar cruise speed. It will drift past Gliese 445 the way a leaf drifts past a rock in a stream, briefly close, then gone. Voyager 2 is heading in a different direction, southward relative to the ecliptic, toward the constellation Pavo in the southern sky. In approximately 40,000 years, it will pass within about 1.7 light-years of Ross 248, another red dwarf, in the constellation Andromeda. Like its twin, Voyager 2 will not pause for introductions. The stars it passes will barely notice. A tiny, cold, silent artifact of alien manufacture drifting through their outer gravitational neighbourhoods, carrying a golden record that nobody on those stars, if anyone exists there at all, will have the slightest reason to look for. Here is a fact that expands the timeline to something almost incomprehensible. In about 296,000 years, Voyager 2 will pass within roughly 4.3 light-years of Sirius, the brightest star in Earth's night sky. By that time, human civilization will either have expanded across the galaxy, or vanished entirely, or evolved into something unrecognizable. The Voyager spacecraft will not know and will not care. They will still be drifting, still carrying their golden records, still intact in the vacuum that preserves all things equally, the magnificent and the forgotten. The golden records themselves are designed to last. The copper substrates, plated in gold and enclosed in aluminum jackets, are expected to remain playable for at least 1 billion years in the interstellar vacuum, protected from the erosion and oxidation that would destroy them on Earth in centuries. 1 billion years from now, the Sun will be about 10% more luminous than it is today. Earth's oceans may be beginning to evaporate, and complex life on the planet's surface may be struggling or gone. The Voyager records will still be intact, carrying Chuck Berry and Beethoven, and the sound of a human kiss through a galaxy that has rearranged itself around them, stars shifting, nebulae forming and dissolving, the Milky Way itself inching toward its eventual collision with the Andromeda Galaxy. Scientists still argue about whether a billion-year timeframe is optimistic or conservative for the record's survival, depending on assumptions about micrometeorite erosion rates in the interstellar medium, but even pessimistic estimates put the lifespan at hundreds of millions of years. Either way, the records will outlast everything their creators ever built on Earth. There is a fringe but charming speculation that occasionally surfaces at conferences and in late-night conversations among space enthusiasts. What if the first entity to find a Voyager spacecraft is not an alien civilization but a future human one? If humanity survives and develops interstellar travel, it is entirely plausible that a fast ship could overtake the Voyagers and retrieve them, the way a motorboat might catch up to a message in a bottle drifting across the Atlantic. The Voyagers would become museum pieces, artifacts of an early, tentative age of exploration, touched by human hands for the first time in thousands or millions of years. The golden records would be played not by aliens puzzling over pictographic instructions, but by human descendants who might find the notion of a phonograph record as quaint and bewildering as we find stone tools. It is a lovely thought, the idea of catching up to your own past. But for now the Voyagers are alone, and they will remain alone for a very long time. Their plutonium is decaying, their instruments are cooling, the hum of the interstellar medium vibrates around them, and the cosmic rays tick against their aging detectors like rain on a tin roof. Sometime in the 2030s, the last instrument will power down, the last bit of data will be transmitted, and the deep space network will record the final signal from each spacecraft. After that, silence. Not the silence of death exactly, more the silence of completion. The Voyagers will have done everything they were asked to do and more, flown past 4 giant planets, discovered active volcanoes and subsurface oceans, photographed rings and storms and moons, measured the termination shock and the heliosheath, crossed the heliopause into interstellar space, detected the magnetic highway and the interstellar hum, and sent it all home on a signal weaker than a snowflake landing on a microphone. They are, by any reasonable measure, the most successful scientific instruments ever built, not because they were the most advanced, but because they were built well enough and aimed true enough to keep working far beyond anyone's expectations. And now the story softens, the way all good bedtime stories eventually do. You feel the edges of the narrative rounding, the pace slowing, the imagery dimming from the sharp brightness of discovery to something gentler, something that asks nothing of you except to breathe and listen. You're still out there, drifting with Voyager, but the urgency is gone. The measurements have been taken. The boundaries have been crossed. The hum wraps around you like a blanket. That low, persistent vibration of electrons in the interstellar plasma, a sound that has been playing for billions of years and will continue for billions more. You're a guest in this sound, a brief visitor passing through on a spacecraft that will outlast your species, carrying a record of who you were and what you loved and what you sounded like when you laughed and kissed and sang. The stars are not closer, they are still impossibly, achingly far. But you have touched the space between them, and that is something no generation before yours could say. The golden record turns silently in its aluminum sleeve, waiting for hands that may never come, and the hum does not mind. The hum has no expectations, it simply is. A frequency, a density, a truth about the medium through which all things travel. Your breathing slows, the data stream thins to a whisper, the spacecraft drifts on, patient and small and magnificent, carrying the best of you into the longest night there is, and somewhere, 17 light hours behind you, a blue dot hangs in a sunbeam, still turning, still alive, still dreaming of the stars. Sleep now, the Voyagers will keep going, they always do.